Welcome to this video. In this video, I will be talking about error correction conditions for stabilizer codes. So in the previous video, we saw what are the error correction conditions, and now we will specialize that to stabilizer codes to show which kind of errors will be correctable in the stabilizer formalism. So we have to understand some mathematics about the centralizer of a group and the normalizer of a group, and then in terms of these centralizer and normalizer we will find the error correction criteria. So let's start. So for before we start, I will warm up with some ideas about the stabilizer group. So I have already discussed what is a stabilizer group, and it's a abelian subgroup of the Pauli group on n qubits that does not contain minus identity. And the idea is we can define, given a set of generators of S, the stabilizer group, we can define a projector onto the code space. So I have also talked about what is the stabilizer code space. It is basically the plus one eigenspace of all the stabilizers that we have. So it is intersection of several different eigenspaces, and let's proceed to understand what is a projector onto the code space. So this is the projector. So the projector can be written as this particular expression 1 over 2m product of all identity plus Si, where Si is the generator of the stabilizer group. So what is the proof of this? The proof is very simple. So the idea is I have 1 plus Si, and if I act it with a state psi, and if my psi is in the code space of Si, this means it is a plus one eigenspace, then it is simple that that it will act in this particular fashion from here to here. So this is the plus one eigenspace condition, and this will give me psi. But if it is not in the code space, so it is orthogonal, it is in the orthogonal space, this means that it gives a minus one eigenvalue, and because every Pauli operator has plus one or minus one eigenvalue, so this means that it will act in this particular way and provide me 0. So this will happen for every stabilizer that is inside the product. So inside this product I have several all different generator of the stabilizer, and because of this it will give me the intersection of the plus one eigenspaces, and the intersection is simply the code space. So now the second thing that we are going to prove is what is the dimension of our code space. So what is the dimension of our code space can be calculated by the trace of the projector, because the projector acts as identity on the code space. And now what we can do is we can simply write the trace as 1 over 2 power m summation over S belonging to the stabilizer group, a trace of S. Now the idea is only one of the stabilizer, which is identity, will have a trace of non-zero, and all stabilizers will be traceless because they are Pauli operators, and this means that basically trace of identity is 2 power n, that is number of physical qubits. So this is my dimension of the code space. So if I have m different generators, so m is number of generators and n is number of physical qubits, then this is the dimension of my code space. So one more thing that I would like to say is this product over all the stabilizer generators can be more precisely written as product of all the stabilizer group elements, because in this product there will be all possible ways in which we can multiply the group elements, the generators together. So with this we come to the centralizer and normalizer of a stabilizer group in the Pauli group of n qubits. So the centralizer is defined in this particular fashion. So an element E belongs to a centralizer of a group if, so this is the definition, E times group element is group element times E, that means it commutes for all G belonging to the stabilizer group. Instead of stabilizer group I can have any group. So this is the definition of centralizer. And what is a normalizer? A normalizer is such that it keeps the group invariant under the conjugation by the element. So I can have E dagger, and it will. So this is the idea of normalizer. So in other words, this is the definition of normalizer. You can act with the element on the set, and you can act from left hand side or right hand side, both will be same. So this is the centralizer and the normalizer, and one can easily see that the centralizer is a subset of the normalizer, because it is trivial to see, because for every element G that belongs to the centralizer, it is also the normalizer, because for particular case of S, the element being as G, so E G equal to G prime E will be a normalizer for all G prime belonging to S. So now let's prove the other way around. So for stabilizer groups, it is true that the normalizer is also same as the centralizer. So this I have shown here. So we are going to prove that the normalizer is same as the centralizer. So how can we proceed? So we already know this. So we know this. Now we will take an element in the normalizer. This means it is of this particular form, such that Vg is equal to G prime V. So G prime belongs to the stabilizer group. Now V and G, they are both Pauli group elements, so they will either commute or anti-commute. So Vg is either equal to Gv, or Vg is equal to minus of Gv. So this means that my G prime is either equal to G, that is they are both same, or they are different by a minus sign. But this is not possible, because if G belongs to the stabilizer group, if G belongs to the stabilizer group, I cannot have minus G also belonging to the stabilizer group, because I don't have minus identity in my group. So this means I only have the possibility that G prime is equal to G, and this means that my centralizer, my normalizer is also my centralizer. So that's what I am showing here. So I started with the assumption that I have my normalizer, and I showed that it belongs to the centralizer. So now let's proceed to see what are the error correction conditions. So I have a stabilizer group, and I have a code space corresponding to it, and let these be the cross operators that belong to the n qubit Pauli group. So these are the cross operators of my error, and if the cross operators satisfy this condition, that is Ej dagger Ek does not belong to, so this is important, it does not belong to normalizer of my group minus the stabilizer, minus the group itself. If this happens, then the errors are correctable. So this is the proof that we will see. So the proof is quite instructive to go through. So the proof is that it does not belong to normalizer minus the group is same as saying that it belongs to the Pauli group minus normalizer plus the group itself. So my error will either belong to the stabilizer group, which is already which kind of means that it is correctable, because the stabilizers are the invariant group elements, or it belongs to the Pauli group excluding the normalizer of my stabilizer group. So if it belongs to the stabilizer group, then I can say with confidence that this holds. So because Ej dagger Ek, it's a stabilizer, it basically kind of projects onto the code space itself. And now if it's the case that it belongs to the Pauli group minus the normalizer, then we have to show that this is also correctable. For this, let's let's suppose that it belongs to this particular group, so it belongs to this. And now what we can do is we can say that it does not belong to the normalizer, means it does not belong to the centralizer. This means that there exists a G1 such that the anti-commutator is 0. So they anti-commute basically. Instead of commuting, they anti-commute. So now what we can do is we can use the projector that we saw before. And basically in the projector we can now operate with EJ dagger EK. Now what will happen is 1 plus G1, which is the element that anti-commutes, it will give a -1 output, and then there will be this. So I have shifted the position of EJ dagger EK by acting on 1 plus G1. And now what I can do is I can again act with the projector, but the projector will have 1 plus G1 somewhere. So 1 plus G1, 1 minus G1 will be 0, because G1 square is identity. This holds for all the stabilizer group elements, because minus identity does not belong to the group. So we are seeing that the fact that minus identity is not belonging to the group is a very important condition, and these errors satisfy this particular constraint, and this constraint is an error correction criteria. So by the error correction criteria we know that this will be correctable, because alpha ij will be equal to 0. So what does it mean is that if I have my errors belonging to the set normalizer minus stabilizer, these errors are uncorrectable set of errors, and they are called logical errors or logical Pauli operators. Now this helps us define in a very formal way what is a distance of a stabilizer code. The distance of a stabilizer code is minimum size, size in the sense that number of, suppose I have x1, x2, x4, this is of size 3. So the minimum size such that my L is a logical error. So the idea is that I have the set of uncorrectable errors as logical errors, and the minimum size of this error will be my distance of the stabilizer code. So that's all for this video. In the next video we will be talking about Hamming code and Steen code. So let's go to the next video.